Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm super happy to have Yuri Cavecchi with us today. Hey, Yuri.
Hi, Frank. How are you?
I am doing well on this July 5th of 2021. It's moist in Phoenix, actually. It rained pretty good yesterday. So our humidity's up. Of course, our heat is always up in July in Phoenix. So, you know, we're up around 105, 106 with a bit more humidity than most Phoenicians are probably used to. So where are you at, Yuri?
I'm in Mexico City.
Okay.
And I have to say this period of the year is pretty rainy too here. So
yeah, we get that Gulf. You probably get it too. You get this Gulf moisture rolling in. Yeah, and it makes it a little bit more humid. So indeed.
Yeah.
So what's your position there in Mexico City?
I actually have started a tenure track. So here at the UNAM, the National University here.
Cool, very good.
So I moved last November, so middle of the pandemic, not exactly the easiest moment to move.
I would say so. I would imagine there was a quarantine or so involved coming in and all that kind of stuff.
Yes, so everything moved a little bit more slower, let's say, even usually, but.
Well, that's great. Well, congratulations.
Thanks.
Do you speak Spanish?
A bit.
A bit.
Luckily, I'm Italian, so, you know, languages are pretty similar.
Yeah.
Maybe I think I speak more than I actually do, but it sort of works. So in that sense, it's
cool. Well, very good. So Yuri, what do you like to do for research?
Mostly, I like neutron stars, and I would say I like computational aspects of astrophysics, and so I like developing code, things like this. And neutron stars have this phenomena like accretion, where accretive fluid can burn, and then has a lot of interesting dynamics going on. So that's basically my main interest, I would say.
Very cool. Nice. And that is going to bring us to this very lovely APJ article on the three-dimensional instability of flame fronts in type 1 X-ray bursts. And Yuri, take us away.
Okay, thank you very much. So yeah, basically this is what I said before. It's in this case, it's only hydrodynamics. There is not magnetic fields, but is fluid dynamics with burning going on the surface of neutron stars. So to say what basically the most probably obscure part in this title is type 1 X-ray burst for people that are not familiar with it. So here we are talking about a neutron star in a binary system, where the companion is a little bit less than 1 solar mass. So there is Roche-Oblet flow, and there is an accretion disk, and matter from the disk goes on the star. And this matter is basically something that comes from the companion, right? So it can still burn through nuclear reaction like it happens in normal stars. And when this burning is unstable, basically meaning a thermonuclear runaway, then you have these incredibly bright X-ray flashes that are the type 1 bursts that we're talking about.
Okay.
And the reason why they are so interesting is that they are actually extremely bright, so you can see them very clearly. They happen relatively often, so you see a lot of them. And and they actually can open windows about various aspects of the physics of the neutron star. So actually, it's very interesting to use them to learn something about what's going on the star. And this can be both nuclear reactions, because as we said, thermonuclear burning, but also eventually, when we finally understand them very well, they can open windows even on the composition of the interior. And maybe I'll touch a little bit this or later in the conclusions, because there are some conclusions related to that. So
nice, very good.
So, and actually, this is one of the nice things about neutron star. Actually, also the nuclear aspects, I mean, they open also conversation with laboratory experiment on Earth. So it's beautiful.
Yeah, and of course, neutron stars are sort of big business these days.
As well. So maybe
post certain LIGO observation.
yeah, maybe there have been some mergers, right, with black holes. So
Yeah,
why not?
stars are front.
They offer everything we want.
Uh-huh.
So, okay, so one of the aspects, let's say, that we are still trying to understand, we sort of have a clear idea, I hope, after this paper, but one of the aspects that we would like, and we are trying to understand well, in order to understand the phenomenology of the burst, is really how the flame propagates, because one idea very important is that the surface will not explode as a one sphere explosion, right? Completely spherical, symmetric. So the burning should start at some location, most probably, especially in non-magnetic systems, on the equator. And so we have to understand how the flame then propagates from there on. It may ignite under certain condition off equator, but for example, in this paper, we're really studying what happens when it ignites at equator.
Okay.
And maybe we can go to the last figure.
Okay.
Slightly non-linearly, but
all
because
good.
that gives an idea of what happens. So we should really look at the top left figure.
Okay, right here.
So the nice and clean one, let's say.
Yes, very clean, looks laminar.
Exactly, it looks laminar, that's the problem. So that's that's the beginning. The idea is that where you see kilometers from 0 to 20, that's from the equator at 0 to pole at 20.
Okay. Okay.
So this is kind of like the northern hemisphere, if you want, a piece of the northern hemisphere.
Uh-huh.
And when you, again, horizontally, where you see from 0 to 5, that's west to east.
Yes.
And one thing, these plots look squared, but they are not squared at all. If you look at the scales, they are actually very stretched horizontally, and vertically, if you read the scale, is 16 meters.
Yeah.
So what here looks kind of a sharp peak near the equator is actually anyway very stretched horizontally.
Okay.
And it's a little bit of a long description of this figure, but the color outside is the temperature, and the color in the cut inside is the nuclear burning rate.
Got
so
it.
It's the energy release.
Got it. Okay. Yes, this is cut out. I'm with you.
Yeah. And so the idea is this, that the ignition started at the equator and the hot fluid expanded. It's very hot, so expanded vertically, and naturally tried to spill, to push towards the poles, both north and south. But one important thing of these objects is that they spin very fast, most of them. They have the spin frequency can be, let's say from 200 to 700 hertz, something like that.
Oh, okay.
So even if neutron stars are only, if you want, 10 kilometers in radius, they are still spinning 400 times per second. It's an incredibly high speed.
Okay.
And the funny and interesting thing is that the Coriolis force basically plays a role. And the Coriolis force creates a current flow that we will see in a second. But that current flow basically confines the hot fluid near the equator, such that the following ignition is just driven by conduction. Yeah. And that's what this nice little picture looks like. And if you don't touch it, this sort of interface will propagate towards the pole unchanged. It will simply self-repeat towards the pole.
Yeah, laminar.
And this description worked very well in explaining kind of the general trend of the observations.
Okay.
But the time scales for the flame to cover the surface were a little bit too slow. to match the observations.
Okay.
If you put magnetic fields, they play a little bit with the Coriolis spores, with the confinement, make it go a little bit faster, but not all the sources have strong enough magnetic field to do that. So we were a little bit on a tight spot.
Okay.
And then we said, well, let's try 3D. Let's see what happens if we perturb a little bit that surface. And you can see in the other picture that a lot of things happen.
Indeed.
And well, we're going to talk about these things. But the main point is that all these horrible or nice things that happen, they actually make, they are not so bad because they don't kill the flame, which is super good because at least, you know, we can still explain a burst. And they make this, the propagation speed actually really nicely fitting with the observation.
Okay, cool.
So that this was a relief. But there are actually many conclusions that comes out of this thing. So we can go back to the beginning and maybe go a little bit more linear.
Okay, very good. Well, I think it's good to put to have a visual picture in one's head. So
yeah, we can go to figure 1, I think.
Okay.
So figure 1 is again, is just a vertical cut of what we just saw. And I'm looking at the green one, sorry, on the right panel. The other one is just the initial condition, but I can describe them by words. So again, once again, this is 10 meters vertically and kilometers, 20 kilometers horizontally, right? So again, the sharp peak is quite not as sharp, is very stretched. The colors here are actually the velocity field.
Okay.
And this is the velocity coming out of the screen. And this is what is the current I was mentioning when I mentioned the Coriolis spores. So here one have to imagine hot fluid near the horizontal zero. Okay. So on the left, the fluid is hot, has expanded. It tried to go to the right, but Coriolis spores bends this motion and takes it basically out of the plane of the screen.
Right. Okay.
This condition happens on Earth actually. The same thing, that the equator is hotter than the pole because of the sun and so on. And there are currents of winds that go towards the east, basically. And it's the same mechanism. So in a sense, it's a geophysics of neutron star, if you want. But there is okay, this wind is this structure of the wind, which is stronger at the higher when it is at the bottom. It's called the thermal wind. But there is an important thing. Here are maybe barely visible, but there are some dashed line horizontally, sort of.
Yes.
And those are lines of constant density.
Okay.
And
okay.
If you want, behind this vertical dashed line, the fluid is hot. So in general, their density is lower than it is on the right.
Yes.
And so basically this gradient of temperature and then of pressure is what drives this wind. But the fact that the density is not constant horizontally creates a situation which is called, basically makes the fluid baroclinic, because the pressure, the lines of constant pressure are not aligned with the lines of constant density.
Okay.
And the fact that ahead of the front, so towards the pole, you have heavier fluid because it's denser, because it's colder, with respect to what you have behind, because it's hot and light, because it's less dense, makes something which is a little bit amazing, because it makes this baroclinic instability possible. And the baroclinic instability is basically like the Rayleigh-Taylor instability, where you have heavy fluid on top of light fluids, and you perturb it a bit, the heavy fluid falls.
Right.
But that usually is in the vertical direction. Makes sense. It's gravity that brings it down. what happens here is that it's again gravity, but it's basically working mostly horizontally
Mm-hmm.
because, as I said, this interface looks very sharp, but it's actually very stretched horizontally. And yet is energetically favorable to swap this cold and heavy fluid parcels with
Yes.
a hot and, light, less dense parcel at the back. And
Very,
what we did is we said, yes, this thing is going to be unstable to this. And we were a bit scared as well, because we wanted to check if this instability was going to kill the flame or not.
right. Strip it, stretch it apart, rip it apart.
Yeah, exactly. No, if you stretch it too much, you may kill it. It may flume out.
Right.
And you saw already doesn't happen. So that was a relief.
Good.
But we also wanted to explore the consequences of this. And we can go to the next slide, to the next page. I mean, the rest is just initial condition where
Initial
basically
conditions.
yeah,
Okay,
we
so
have
figure
some-
two.
Yes, figure two. So just one note, we're burning helium, just so to say. So figure two is a bit technical, so we can go very quickly. It's just that we were saying, and we were expecting this baroclinic instability to take over.
Mm-hmm.
But as we saw, there is this wind structure, which is also, there is a lot of shear that can lead to other instabilities. But yes, but basically this is the growth rate of the instability, which matches, the blue is what we measured in the observation. And the dashed line is theoretical one for baroclinic instability. It's from a simplified baroclinic instability, so it doesn't apply directly, but it matches quite well. So that's one confirmation. But the best confirmation is the next figure, I think, figure 3 on the
Find front instabilities and figure 3. Okay.
It's the next page.
Figure 3?
Yes, this one, basically. Here we are looking at the west-east direction horizontally.
Okay.
And the vertical direction.
Okay.
And for people that study fluids in the ocean and in the atmosphere of the Earth, they see this and they say baroclinic instability.
Yes.
Because so what is here is the temperature at the top. The velocity in the middle is the velocity going towards the north. So
yes,
yellow is towards the north and purple, dark blue is going towards the south. And at the bottom is velocity in the vertical direction. So again, yellow is going up and dark is going down. And this misalignment between the contours of velocity and temperature at the top is actually basically one of the smoking gun of this baroclinic instability, because there is a net motion of fluid which is going towards the north and up, bringing the hot matter in this direction, and vice versa is bringing cold matter south and down. And this is this horizontal mixing that I was mentioning about, which works a little bit vertically because these surfaces of density are a little bit inclined, but mostly works horizontally.
Yeah, I mean, there's 2 orders of magnitude difference in the loss.
Yes, exactly.
Right. Okay.
And it's amazing, but it's still tapping on gravitational potential energy, because if you're bringing cold fluid, which is denser, you're lowering the overall barycenter, if you want, of the fluid, and you're releasing gravitational energy into kinetic energy in this motion.
Cool. Very nice.
And so let's say this was also one of the smoking gun, because Anatoly, his co-author, is plasma physicist. They like their instability, but they like also to be exactly sure about which instability we're talking about.
Okay.
And so we were looking for different proof, but this one I think is really a smoking gun of that.
Nice. Very good.
That source. But then we go, yeah, this is more details about how the motion of the fluid is, and you can see the same corrugation.
Okay.
But we can go to the next figure, and that's where actually things become interesting for the type 1 bursts.
Okay.
Because again, we have a few, we had, if you want, for the propagation itself, a few questions. Can the flame survive, but also can we speed it up?
Mm-hmm.
And this is the early stages of where before there was the instability still in the linear phase. Here is saturating. So like there we have like 5 modes, but here the one mode is basically dominating.
Helium.
Is catching up. And what I'm plotting here at the top, these are horizontal cut. So we are looking from the top, we are looking to the surface of the star, and we have the composition. And composition means blue means burnt fuel, and red, orange is fresh fuel that can be burnt.
Propagating this one. Yep.
And in this case, is helium mass fraction. And at the bottom is temperature. So again, red, orange is hot, and blue is cold temperature. And here we start seeing basically the flame front, basically where the dash line is becoming to be perturbed by this growing instability, no?
Yes.
And what this instability does, it actually, in a sense, helps the flame, because we can see in the next slide that sorry, I say slide, I mean figure.
Yeah, I understand.
It's yes, here the instability has developed quite more dramatically. But what it does is that it brings some of the fuel that can be burned, it brings it back. Yes, it brings cold fuel, but it's still very quickly burnable. So that doesn't kill the flame. But on the other hand, it brings hot fluid ahead.
Yes.
And I can basically already tell you that that's what's making the flame goes faster, because conduction is slow, right? But we have to match like from 1 to few seconds rise time, and to cover the surface of a neutron star in that time with pure conduction is difficult. Now we have this stretched interface horizontally, which makes the conduction work a little bit faster, not per se, but because the surface of conduction is so big. But the instability brings in mechanically, if you want, hot fluid ahead.
Okay.
It allows this hot fluid to start already eating up the cold fluid ahead. And basically, it's really the mixing and the mechanical action of the instability. We are tapping on the gravity of the neutron star for the kinetic energy, and neutron stars have a lot of gravity. So that makes the flame go faster.
Nice.
One interesting thing that it starts to appear here is, so exactly in the temperature plot, there are these arrows and lines. Those are streamlines. And you can see that the fluid is starting to create rotation vortices.
Yes.
Where they go some in one direction, some in the other.
This way, that way. Yeah.
And that's exactly. And those behave like, so that's an anticyclone, basically where you are now. So in the red part, that's an anticyclone. And in the blue part, there is a cyclone developing. And again, to make a parallel, somebody that deals with ocean may see, oh, I know those structures and those kind of perturbation, because they also happen on Earth under different circumstances, if you want. But since the basic mechanism is the same, we are triggering the same phenomena as in
that's nice.
as on Earth. Yeah, no, it's amazing, because they are completely different objects, right?
Sure.
One solar mass or two in 10 kilometers versus the mass of the Earth, which is much bigger and less mass, and yet the same phenomenon.
Yep.
But then we can go to the next one. And here things are getting messy.
These are definitely evolving at this point. These are,
And,
okay.
and again, it's the composition on the left and the temperature on the right.
Yes.
And here we are just following the evolution through time. And yes, so at the bottom, at the top, there are these cyclone and anticyclone that are forming.
Mm-hmm.
But then the structure break down as we start seeing the middle panel, and as it's clear in the last one. And they launch these blobs of hot fluid that is circulating in this case, it's an anticyclonic way, and this alternation of cyclonic and anticyclonic structure. So if they're centered on the hot fluid, they are actually higher in density, they are anticyclone. And when they're centered on cold fluid, they are cyclonic.
Uh-huh. Very cool. Nice.
And you can see the structures in, I mean, one-to-one, let's say, also in the composition. Of course, the hot ones are burning more, so they are bluer, let's say, in the composition.
Yes.
And the other are more lighter, green or yellow because they're colder. But since you have this mixing, let's say, of the hot fluid, that's what's make the flame goes faster. And we form this cyclonic structure because Coriolis force is still very important, right? Across all the surface. Actually, so here we slightly cheated because we kept Coriolis force constant. But anyway, going towards the pole, it would be even stronger because Coriolis force is basically absent at the pure equator, strongest at the pole.
Yep.
So this Coriolis force basically creates these hurricanes, but again, confine the hot fluid. And that's also what helps it survive, because you don't launch just a blob of cold fluid that will spread completely across the surface, but you keep it confined in these anticyclones.
Nice.
So when it has time to heat sideways, it's the cold fluid and brings it much faster, let's say, forward.
Good.
And so I think this solved, for example, one aspect, right? So this matching the rise times. So the matching these observations.
That's right.
So it seems like now we have this sort of basic, I'm going to be bold and say solid understanding of the propagation, both in magnetic and non-magnetic systems.
Okay.
So, of course, when I say solid, I mean, maybe I shouldn't say really totally solid, that there is a lot of work to be done. This, as I said, is a constant Coriolis force. Maybe it's just one case. We should study more cases, of course.
Sure.
And but this is a good beginning.
It's a good beginning. There we go.
let's put it like this. And then the other figure helps me discuss another aspect, which is, I think, very interesting, because the first aspect is more related about, it could be related to studying the nuclear reactions, because also if we understand the phenomenology, maybe of the rise time and the distribution of the flame, we can really start to make a strong comparison between the theory of nuclear burning that we have from Earth to the observations of the neutron stars. But as I said, the burst can also be used maybe to learn something about the interior composition, the composition of the core of the neutron star, which is really where, physical theory go a bit crazy, in the sense that we don't know actually how it works. And there's a
The
lot
equation of state of cold dense matter. Yes.
Exactly. So it's a lot of
and transport properties, I should say. Yes.
there's a lot of work and a lot of interesting things to be done. And so any way we can find to measure some information about it, it's great. And the burst can offer some information about that. So what I'm plotting here, it's the height of the fluid, which again, if you see, again, red means very high, blue is lower height. And you can see that.
I see. Okay, this is the vertical height.
Is the vertical height.
I'm with you. Okay, I'm with you. Okay.
And so basically what can be seen is that it tracks mostly these hurricanes, right? This is early stages growing forward. Especially by the late time, we see that there are these vortices still there. It has increased a lot, height, and they distribute sort of regularly. That the size of those vortices depends on the spin of the star, basically. And yes, and on the temperature of the burning, but since that's given, let's say it depends on the spin of the star. And they form with a regular structure. Now, let me go a little bit sideways and explain how we can use the burst to learn about the equation of state. One of the ways is to measure the mass and the radius of the neutron star, because those depend basically on the composition of the core, which is what we don't know. So we have a theory, we build different ranges of mass and radii, and then we look in observation. The ones that match the observation are the correct theory. That's the simplified approach, right? But we need to measure the mass and radius. Now, mass is relatively easy. For example, with pulsars, we know binary orbits, or with the gravitational waves very recently, right? Mass sort of come out. Radii are a little bit trickier to measure.
Yes.
And one thing nice about the neutron star is that, of course, the general relativity is important. Their gravity is so strong, they're so compact, that the photons that leave the surface, they have to fight against the gravitational potential in a way that leaves an imprint of the gravitational potential in the observation. And especially if there is some asymmetry in the emission, this asymmetry creates pulsation, like a lighthouse. So if you have a big blob on the surface, which is brighter, when the star spins, the blob points to you, the lighthouse points to you, you see a little bit more light. When it goes away, you see a bit less.
Sure.
Now, this going up and down is modulated by different phenomena that depend differently on mass and radius.
That's the key.
That's the key. And if you can measure the shape of this pulsation, you can engineer back mass and radius. This is what's been done actually incredibly, I think, effectively by the NICER satellite that was using the same technique. It was using not the burst oscillation, it was using pulsation from neutron stars that are accreting but with a strong magnetic field, so they have an hotspot due to the accretion. But for example, what came out of their work is that the emission pattern they were expecting is not as nice, as simple as they expected. It's actually amazing how they could reconstruct the emission pattern. They were expecting to basically antipodal hotspot. They found, for example, in the first paper, they found a half moon on one side and a small hotspot on the same side. So that was an interesting thing. But the burst in the light curve, they also show pulsation, especially when the surface is cooling down. And so they also show pulsation. So the same technique can be applied using the light of the bursts. But as we saw in NICER, it's important to know the emission pattern. I mean, it helps a lot in reducing systematics in your interpretation of the data, because then the only unknown is the mass and the radius of the star.
Cool, nice.
But which patterns are on the surface, that's a little bit still debated, let's say.
Yes.
Main idea, especially in the tail, is that there are some ocean waves, and these waves create a pattern. But especially which kind of waves, that's a little bit tricky, and that's debated. And also these waves don't fully work. But what we see here is these hurricanes. And here we go back finally, sorry, I took a long tour. But so these patterns, so here the vertical, if you want, direction is X, so that's west-east. So
Yes.
this pattern already can give you a modulation in the light curves. Personally, I'm not sure that these are responsible directly for the burst oscillation, because I think they are a little bit too repeating to give you what you will really see in the burst oscillation.
Okay.
But what they can work as, they could be the hammer that hit, if you think about the surface as a membrane, they could be the hammer that hit in specific point, the membrane, and therefore excite specific kind of waves.
Yeah. Mm.
And specific kind of oscillation. So these could be related to could be what triggers the oscillations.
Uh-huh.
And so this again is opening maybe another possibility, maybe, continuing the use of this simulation, maybe adding more physics, and it could describe better what happens to the fluid next. This could go into the direction of the burst oscillation, which will help again eventually for the mass and the radius. So we were extremely happy about these results. I think the hurricane especially were a bit unexpected, but very welcome.
That's always nice.
Yes, yes. And
very good.
Yes, and then the paper finishes with some pictures of comparing on the improvement, but these are just details. It just shows that the flame spreads much faster, and it actually shows that it is a little bit, but you really need 3D. What this last figure shows is you really need 3D, because the first column is for the 3D case, the 3D unstable case.
Okay.
When we did the instability, it's average composition, average temperature, and average nuclear reaction rate versus what you see in unperturbed simulation.
Yes. Okay.
And the middle column is if you take the same time, and the main thing you see here is that the flame is way behind if you take the same time, so in the middle column, and also that it has a much clearer gap between the part that has basically burned completely and the part which is still to be burned. Yes. This is easily seen in the top figure. And the last column shows, again, an unperturbed simulation at the position where roughly the flame is at the same position as in the perturbed simulation. So comparing the first column and the last one, the flame is roughly at the same position horizontally. Right. But again, the structure is very difficult. And we wanted to see, can we somehow go from, 2D unperturbed simulation and do maybe some easy trick to say maybe computational time? No, we cannot. That's the point. Okay. No. So, okay, that's a little bit bummer, but I think the other conclusion, especially the vortices, were good enough. But they definitely gave a positive spin on the spinning neutron star results.
On the topic, absolutely. Very cool. Very cool. Well, Yuri, thank you very much for walking us through your lovely APJ article.
That was pleasure.
And let me ask you, where do we go from here? Are there, for example, additional NICER observations coming? Are there different satellites that can look at some of the different high energy emission that can shed some light on the topic? Are there additional, and I understand there's always additional calculations to do, but you hinted at a couple of directions where one might want to take this. So just sort of where do we go as a community over the next 5 years or so on this topic?
Yes, it's. I think the future is bright, as you say, right? There is definitely NICER, which is providing extremely good observations also of type 1 births. And it has a nice both timing and also energy coverage. So we can see different aspects of the birth. And so that's definitely providing nice observation. And there are future satellites. There is one NASA satellite, is Throwbacks coming. So
okay.
Proposed. So that's very nice. Another one is more European and Chinese. It's called EXTP. They both explore some aspects. So observation-wise, let's say we have to wait a bit, but future is bright.
Cool.
And simulation-wise, as you said, is there's always things to do. No, there are a few groups working on the propagation of the flame, like. Well, I'm working in, but also a group of Mike Singali at Stony Brook, basically, and well, we're also collaborating. So it's it's nice. But there are definitely aspects. As I said, this is one case we have to see if there are, for example, limits between the spin. If maybe not all the spin are enough to sustain the flame or not. And magnetic fields are always behind the corner, right? They prove to be good in one sense, but how they will interact with these vortices and so on, that's, I think, one of the most interesting things to explore. Yeah, so.
Nice. All right. Lots of stuff to do.
Yeah, but I think we are really getting to the position where the simulation, if you want, the theory and the observation can really start again, talking effectively to each other. So
good. Good.
So super good. I think super good.
Awesome. Yuri, thank you once again.
Thank you.
And everyone, thank you very much. And I hope this made your astronomy day just a little bit better. Thanks, and we'll see you on the next one. Bye-bye.
Bye-bye.